Hello, I'm Yaman from Xilinx Research Labs, and today I'll be talking about LogicNets, our recent work on co-designing neural networks and circuits for extreme throughput applications. This is a joint work with my colleagues Nick Fraser and Michaela Blott, as well as our intern Yash Akhauri, who is now at Intel Labs. I'd like to start with a single slide summary of what you'll be hearing about from me today. LogicNets is a co-design approach where we design specialized DNN topologies that translate directly into a high-performance FPGA implementation. So let's say we have some task at hand that we want to solve using a neural network. First, we'll define and train a specialized DNN topology subject to particular constraints in a machine learning framework such as PyTorch. With LogicNets, we can directly convert this trained network into an FPGA circuit. This FPGA circuit is a fully parallelized implementation of the trained DNN, and is able to achieve very high throughput and low latency owing to the constraints we put on the topology. As an example, we can classify incoming packets on a network interface as suspicious or not suspicious with a throughput of over 450 million packets per second in less than 10 nanoseconds of latency, with an accuracy of over 90% and using only 16,000 LUTs. Now, the kind of applications we target with LogicNets are a bit special. So I want to tell you a bit about what we call ML and extreme throughput applications first, to motivate our approach. When you hear about ML or DNNs, the first thing that comes to your mind may be applications in computer vision, like image classification and semantic segmentation. While DNNs are indeed very popular for computer vision, the promise of how neural nets and machine learning will change our world extends far beyond that. So let's go back to the basics for a second. The paradigm shift that comes with machine learning is all about replacing manually programmed implementations with learned implementations. So instead of writing programs manually to solve the problem at hand, we can instead gather many input-output examples to form a dataset and use machine learning to learn a good neural network model that solves our problem. As you can imagine, this is a quite generic idea that is applicable to all sorts of tasks and many domains beyond computer vision. And if you work in a particular application domain, you may have already witnessed neural nets starting to replace manual implementations in your domain. Now, one type of domain FPGAs have been traditionally pervasive in is this type of application that needs to process huge amounts of data in real time. For lack of a better term, we're going to call them extreme throughput applications in this presentation. And what we're seeing in some of these extreme throughput applications is a trend towards replacing manual implementations with DNNs. Here's 3 examples to make this a bit more concrete. So here's one from large-scale, high-energy physics experiments like those at CERN, where we want to filter through huge amounts of data coming in from particle collisions to focus on what's interesting. One from intrusion detection in wired networks, where we want to examine incoming network packets to detect whether they may be sent with malicious intent. And one from wireless communications, where we want to replace manual signal processing algorithms for things like digital pre-distortion with neural networks. So, given that applications like these have to go through gigabits to terabits of data every second and make decisions based on it within microseconds, how do we mix DNNs into such extreme throughput applications and make sure that they're running fast enough? To help answer that question and put our work into perspective, let's examine what some of the existing solutions for neural network inference on FPGAs look like from the perspective of specialization. We'll visualize this on a rough spectrum, where we have solutions which are much more flexible and generic to the left, but are usually slower as a trade-off. And on the right, we have the solutions that are much more specialized and require more design effort, but can run much faster as a result. One quite popular alternative on the left side is to create a fixed architecture programmable overlay on the FPGA that is operating with some fixed parallelism and arithmetic precision. We take this fixed architecture and generate a program for it to execute our DNN layer by layer. This can support a broad range of DNNs, but comes with limitations of the von Neumann bottleneck as the price of its programmability. There are many examples of this approach, ranging from papers presented at FPGA conferences to Xilinx's own Vitis AI product offering. For applications that demand more performance, the FPGA research community has proposed custom data flow architectures that offer great performance and efficiency, especially for quantized networks. These approaches typically have a library of neural network components that they can instantiate with flexible parallelism and arithmetic, taking advantage of greater customization for higher performance. Some examples here are HLS4ML, LogicNets, and RevNet, as well as our lab's own work on Fin. And finally, for the extreme throughput applications that we consider here, which may need even higher throughput and lower latency than what can be provided with those other solutions, we need to take customization one step further and co-design the neural network topology and the circuit we're deploying so that we can translate our DNN directly into an RTL circuit with fully unfolded, pipelined, feed-forward data paths. And this is where our work on LogicNets comes in. So, now that we've covered the why, let's start talking about the how. How can we customize our network such that we can run DNNs at 100 millions of inferences per second? Let's take a bottom-up approach to answering this question. As the performance demands for extreme throughput applications are so high, we have to utilize the available hardware to its full potential. This is the question that drives our methodology. Given that the building blocks of FPGA hardware are small truth tables that can implement any function, how can we design DNN topologies that map well to these building blocks? Here's a 6LUT, capable of implementing any function with 6-bit inputs and 1-bit output. Could we somehow construct something in a machine learning framework, such as PyTorch, which is trainable with standard DNN training methods and that maps directly to this bit of hardware? The answer is yes, we can. Neural networks are built out of neurons, and if we have a neuron with quantized inputs and outputs, we can utilize the equivalence of quantized neurons and truth tables to do this. For instance, if we have this neuron trained in PyTorch with a total of 6 inputs, each quantized to a binary value to give a total input of 6 bits and a quantized output of 1 bit, we can always convert it into a single 6LUT by enumerating each possible input and observing the output to construct a truth table. Note that the artificial neuron can have floating point weights and complicated functions such as batch norm inside it. All that matters in the end is the total number of input and output bits. In LogicNets, we refer to the PyTorch implementation on the left here as a neuron equivalent, or NEQ, and the hardware that this neuron maps to on the right as the hardware building block, or HBB. Finally, let's keep the hardware cost of implementing this NEQ in mind. So for this case, we'd have to spend 1 6LUT to implement this PyTorch graph in hardware. From a hardware cost and performance perspective, this is great because a single LUT is very cheap and we can run it at it extremely fast. And of course, we can extend this concept beyond 6 binary inputs and a single binary output. And we want to, because 6 binary inputs can be quite limiting. In general, if we train a quantized neuron with a total of X bits of input and with a Y bit quantized output in PyTorch, even with floating point weights and complicated functions like batch norm, we can apply the same enumeration procedure to convert this into a truth table with X inputs and Y outputs. But we need to consider the hardware cost of this. How many 6LUTs will this cost? You can read more about this in our paper, but in general, we can say that the worst case cost of implementing a truth table with X inputs and Y outputs will be proportional to Y times 2 to the power of X. And that hardware cost function we just came up with tells us that we have a problem. We have an exponential in there. The total fan-in X of our neuron introduces an exponential implementation cost for scaling to more inputs. For instance, a single neuron with 4 times 3-bit inputs and a 3-bit output would require a much larger table built out of about 4,000 6LUTs for the FPGA implementation. Now, this isn't too bad by itself, but we want to be resource conscious here because we're going to have lots of these neurons in our network, and we don't want to have an explosion in the number of LUTs. Our solution to this in LogicNets is to co-design the topology with a feasible FPGA implementation in mind, such that we can avoid an intractably large number of LUTs. So how do we avoid the explosion in LUTs? Recall that the fan-in X of a neuron is raised to a power of 2, so the most important thing is to keep X reasonably small in the topology we design. There are 2 contributors to fan-in, how many connections we have, and how many bits each connection needs. So we use 2 key methods in LogicNets to design topologies with low fan-in. The first method is to ensure that the network is highly sparse, so that each neuron in each layer connects to only gamma previous neurons. The second is to use low-bit activation quantization, such that each neuron produces a beta-bit activation. These parameters, beta and gamma, are knobs we adjust empirically, but just to give you an idea about their range, in LogicNets, we constrain beta times gamma to be less than or equal to 15 to keep the LUT cost reasonable. So for instance, we might experiment with a sparsity of 7 with an activation quantization of 2 bits. So to control the fan-in, we have to control the sparsity. How do we do that? There are multiple methods in the deep learning literature, including a priori fixed sparsity, which is defining a random fixed sparse connectivity at the start of training, which doesn't change during training. Iterative pruning, where we gradually prune the smallest valued weights during training, as well as more advanced methods like sparse learning, where we prune weights based on magnitude and regrow based on some principle. In this work, we opted for a priori fixed sparsity since it was the simplest to implement and still gave us decent results. It's worth highlighting that LogicNets is actually agnostic to how we make the network sparse, so long as the number of connections per neuron can be made small. So we could use any of these sparsity techniques in theory. The other key element in controlling fan-in is activation quantization. There are also many ways of doing activation quantization for neural networks, but we're mostly interested in few-bit quantization, where beta is typically less than 4 to keep the fan-in small. And in that case, we need to use what's called quantization-aware training to keep the accuracy. In this work, we use Bitwidth to obtain uniformly quantized activations, using the quantized hard tangent for binary activations and the quantized ReLU for multi-bit activations. Bitwidth is a PyTorch library from Xilinx Research Labs for quantization-aware training and is open source on GitHub, available on the link you can see to the bottom right. Now, we have all the parts, and let's put it all together with a small example to show what a LogicNets neural network topology looks like. In this example, we're going to design a small multi-layer LogicNets perceptron with 3 layers, with 64 neurons in the first layer and 32 neurons in the other 2. Let's choose a sparsity factor gamma equals 6, which means that each neuron in each layer will receive 6 random inputs from the previous layer. To keep the fan-in small, we'll choose the activation bit with beta to be equal to 2. So each neuron in our network will produce a 2-bit activation. And I'm also going to assume my inputs are also quantized to 2 bits in this case, for simplicity. In this topology, the fan-in per neuron is equal to 6 times 2 equals 12 bits. And each neuron is producing 2 bits, so we have these 12 by 2 NEQs inside each layer. In turn, each of these 12 by 2 neurons is going to receive 6 2-bit inputs, multiply it with floating point weights, pass the weighted sum through batch norm for faster convergence during training, and then produce a 2-bit activation using quantized ReLU. Now, using our hardware cost model, which you can read more about in the paper, we estimate the cost of one such neuron to be about 170 LUTs. Multiplying this by the number of neurons in each layer, we can get the per layer hardware costs. And finally, we can sum across the layers to arrive at a total cost of 21.6 thousand LUTs for the entire network. It's worth noting that this is a worst case cost due to a very simple cost model, and in practice, we'll need much fewer LUTs thanks to synthesis optimizations. To facilitate explorations of LogicNet style topologies, we have built a prototype design flow in PyTorch that allows the user to go from topology to training to FPGA hardware. The first step in this flow is to define a topology of NEQs in PyTorch by instantiating sparse and quantized layers of desired sparsity and activation quantization. At this stage, it's also possible to run the cost model to get an estimation of how much FPGA resources will be needed, which provides valuable feedback to the machine learning engineer without having to go through full training and synthesis. After the topology is decided, including its number of layers, neurons, sparsity, and activation quantization, it's trained in PyTorch with stochastic gradient descent, in the same manner as any other neural network would be, in terms of hyperparameter optimization. Once the desired accuracy is reached, our tool flow automates the conversion of each quantized neuron in the topology into a truth table by enumerating each possible input combination, evaluating the trained neuron, and entering the result into the truth table. Finally, this truth table is converted into Verilog code, which is ready for synthesis with Vivado, either as part of a larger system or as a standalone component. And now let's have a brief look through some of our results to see what we can do with the LogicNets approach. To evaluate LogicNets, we've focused on 2 tasks with extreme throughput requirements that we discussed in the beginning, one from high energy physics and one from network security. I'll briefly cover the properties of each task in the next slides. Because it's not possible to know how accurate a given network topology will be on a given task without actually training it, we've chosen to structure our evaluation as a design space exploration of relatively small topologies so that it became feasible to run lots of training experiments. To help us focus on the relevant part of the design space, We used our hardware cost model to guide the setting of beta and gamma. All the results I'll be presenting here are generated with the LogicNets flow presented in the previous slide. First defining the topology and training in PyTorch, followed by Verilog generation and Vivado out-of-context synthesis, targeting a Xilinx VU9P FPGA. The first set of results I'm going to share with you is on the jet substructure classification dataset, which was also used in the original HLS4ML paper by Duarte et al. This is a 16-input, 5-output classification problem from the high-energy physics domain, where the goal is to help filter the interesting particle collision data at CERN LHC triggers. Here is a subset of results LogicNets achieves on this task, with increasingly larger designs as we go down the rows. Let me start by highlighting this top row here, which is able to achieve a non-trivial classification accuracy of almost 68%, using only 214 LUTs. This very compact resource footprint is due to a fan-in of 6, which translates into a single LUT for each neuron. The Fmax here is reported by Vivado as over 1.5 GHz, which isn't feasible in practice, so we take the global clock network frequency limit instead. Since these are fully parallelized, fully pipelined designs, we'd be able to achieve 666 million inferences per second with this design. Continuing our exploration, as we make the network larger by using more layers and a fan-in of 12, we're able to achieve an accuracy of almost 72%, using about 38,000 LUTs and reaching a performance of over 400 million inferences per second with a 13 nanosecond latency. Comparing this with the FPGA results by Duarte et al., we see that we compare quite favorably on the performance and FPGA resources front. Namely, our design is able to achieve 1.9 times higher throughput and 3.8 times lower latency, using no DSPs and less than half the LUTs of the Duarte et al. Design, which uses 16-bit arithmetic. At the moment, this comes at the cost of minus 3.2 percentage points accuracy for LogicNets, but this may be remediable by using a larger network or if the performance accuracy trade-offs are found acceptable by the domain experts. Now let's have a look at the LogicNets results on the network intrusion detection task, which are trained on the UNSW NB15 dataset by Mustafa et al. The task here takes the shape of a 49-input, 1-output classification problem, where we're looking at features derived from network packets in order to classify the packet as malicious or not. You can see some highlights from LogicNets designs on the table to the upper right, where we see a trend similar to the jet substructure classification results. In particular, by using smaller networks with as few as 2 layers and neurons with a fan-in of 14, we can offer high-throughput intrusion detection as fast as the global clock network will allow, offering close to 85% accuracy using only 3,500 LUTs. Such LogicNets could be suitable for small footprint intrusion detection on FPGA-based SmartNICs and similar. Further down the table, by moving to bigger networks and larger neuron fan-in, we're able to achieve higher accuracy at the cost of more resources. Comparing the results in the highlighted row versus the results by Murovic et al., who deployed binarized networks for intrusion detection on the same dataset, LogicNets are able to offer improvements across the board. Specifically, we are able to achieve 9.2 times higher throughput, with 1.9 times lower latency, using 3.2x fewer LUTs, and with 1.2 percentage points better accuracy. Although there's much that we don't yet understand in terms of exactly how to design LogicNet-style topologies with a very high degree of sparsity and quantization while retaining accuracy, there is one final aspect of our results that I want to highlight, and that is regarding the impact of activation bitwidth. In general, we would expect bigger topologies that use more FPGA resources to always perform better in terms of accuracy, but our results indicate this isn't always the case. Some of the topology choices are crucial to achieving good accuracy, and we found the activation bitwidth beta to be one of them. Let me explain this on the scatter plot here, where we have the model LUTs on the x-axis, a measure of accuracy on the y-axis, and each point here is a trained network with a certain number of layers, sparsity, and activation bitwidth, where the 1-bit activation results are highlighted in blue and the 2-bit ones in red. What I'd like to draw your attention to here is this bit. If we're looking for a model that requires a few thousand LUTs, 2-bit is a much better choice. Namely, we can get about 4 percentage points more accuracy for the same amount of LUTs. Notice that the accuracy for 1-bit results tapers off around 85%, and simply adding more neurons or connections at 1 bit isn't sufficient to increase the accuracy. If you're curious, we have more data on the impact of activation bitwidth, synthesis optimizations, and much more in the paper. In conclusion, LogicNets is a co-designed method to deploy neural networks as part of extreme-throughput applications. By leveraging the equivalence of quantized neurons and truth tables, and exploiting sparsity combined with few-bit activation quantization to keep a compact circuit size, we were able to demonstrate 100 millions of inferences per second on 2 simple datasets. Due to the cross-stack nature of LogicNets, there are many exciting directions for future work here. On the machine learning side, we would like to improve our understanding of how to design highly sparse and quantized topologies that retain high accuracy, whereas on the toolflow and EDA side, it would be great to have better synthesis techniques to scale to neurons with larger fan-in. And of course, on the application side, to discover and demonstrate more extreme throughput applications that can leverage LogicNets. And last but not least, I'm happy to announce that we're planning to release LogicNets as open source as part of the Fin ecosystem. So stay tuned for more updates on the Fin project page linked here if you're interested. This concludes my presentation. Thank you for listening.